I'm going to go ahead and launch in here. I think today, I hope today's an interesting meeting, and I think we're going to have some exciting topics for discussion, both on CalTrack 2.1 and on the future of the working group. And especially on that latter topic, I'm looking forward to getting just kind of an open discussion going if folks have thoughts or even feedback on how this working group has gone to this point for the development of CalTrack 2.1. And so just taking a look at an agenda for today, we're going to talk about something that I think we've mentioned a number of times, but we haven't really shown any data to verify what we've been saying. But we want to at least hit on running CalTrack 2.1 in 2.0 mode and actually compare those outputs to those of CalTrack 2.0, like the actual CalTrack 2.0 that is currently in the OpenEEmeter codebase. And talk about why we think it's important that we retain the ability to run a CalTrack 2.0 style model. And I'll just give a little teaser. If I was a betting man, I think I would bet that the majority of instances that CalTrack 2.1 is run, it will actually be run in 2.0 mode. And we'll talk about why we think that is. And then we have some near final testing results on CalTrack 2.1 that we can go over. I don't think folks will be surprised by anything we show there, but we do want to continue to dive into other kinds of use cases. For instance, we've focused mainly on gas meters to this point, but we have some results that we needed to look at for commercial meters as well, and electric meters. Then we want to revisit a topic that we've planted some seeds around early on, and we finally ourselves have had a chance to come back to this topic and do some validation with respect to an adaptive loss function as a means to optimize models, as opposed to a standard sum of squared errors or just mean bias error optimization approach. And then we want to just lay out the final steps that we think are left in the CalTrack 2.1 process, at least related to the daily model itself. And I think we're thinking right now just about the model that we've developed. However, there are a few outstanding topics, things like delivered fuels, that I know are still kind of out there, and we need the group to convene on those topics again. And then finally, I think hopefully we'll have a good amount of time, and I expect that we will, for this last topic, which is what comes next in the working group. And we can probably start out that just getting some feedback and ideas about kind of what's worked, what hasn't worked, how folks are viewing this whole process. And then we do want to dive into just like laying some conceptual groundwork around CalTrack 3.0, the hourly model, where that can be improved, because that's an area that I think is ripe for further development, as well as potentially open source, like the whole open source paradigm, consolidating a lot of the written methods and the code, and bringing other things into the OpenEEmeter framework, for instance, comparison groups as well. So I think we're at a point where we would see some real advantages of consolidating a lot of the open source code that exists, that are currently in different repositories, bringing them all under the OpenEEmeter umbrella. But there may be some disadvantages to that as well, and we don't want to make any presumptions there. So we definitely would like to just kind of open the lid on that topic and get some feedback from folks here. Okay, so this is probably the least sexy, but one of the most important topics that, it's kind of amazing that it's only now that we're really like showing results on this, but we've been saying take our word. So this is what we mean by take our word. So this is a histogram of every single data point that we've measured across the 6,000 meters that have been the subject of CalTrack 2.1 development. And this is a difference between those data points, their baseline model that was generated by the old Caltrack 2.0 model versus the new Caltrack 2.0 model. And obviously, right off the bat, there are some differences. I mean, this histogram is not just a single bar that, you know, goes to infinity at 0. There are some differences data point to data point. And why are there differences? Well, there are differences because we have a different optimization approach in Caltrack 2.0, or in Caltrack 2.1, operating Caltrack 2.0. We got to think of a better way to say that. And namely, it's that we've gotten rid of the grid search. So we would fully expect that there are some differences, data point to data point to data point, between the baseline model that's developed in Caltrack 2.1, operating in Caltrack 2.0 mode, versus the original Caltrack 2.0. We've also eliminated a few bugs that were in Caltrack 2.0 old mode, like little spikes that were occurring in the baseline model. Those are no longer present in the new formulation of Caltrack 2.1. And then finally, Travis has done a lot of work implementing these elastic net regressions, and that has sped up the model dramatically, along with eliminating the grid search and instead using a global optimization function. And all of these things combined mean that we have a different model. However, the question is that model producing basically the same results? And the answer is yes, it is. You can see that the mean fractional difference between these two models is, you know, well under 1%. It's actually under 1/10 of 1%. And the median difference is even smaller than that. You know, under, you know, 1/10 of a percent. You know, 2/100ths of a percent. And so you can see that despite the fact that, you know, there are some differences data point to data point, the distribution is extremely symmetric. And all in all, you have a model that's going to perform nearly identically at a population level, especially, and even really on an individual meter level. So let me just stop there, see if there are any questions. And just as a reminder, the reason this is so important is in many cases, you know, we still believe that you'll want to be running a Caltrack 2.0 style model without the kinds of seasonal splitting or weekend weekday splitting, because many data sets are monthly data. So, you know, for those who've been part of the working group since day one, you'll know that we've talked a lot about avoiding overfitting and really paying attention to how many parameters you're introducing into a model, and minimizing the number of new parameters with penalization functions and cross-validation and things like that. Well, when you have only monthly data, you only have 12 data points. So splitting a model into seasons, obviously weekend weekday splitting is not even possible when you just have monthly data. But we still want to give people the advantage of the speed and the computational efficiency that we offer now through Caltrack 2.1. So we need to retain the ability to run these 2.0 style models. So that's going to be part of the code package. And again, this is just staring at this histogram, looking at these statistics. We just wanted to validate and prove to everybody that you should have confidence in when you're running on monthly data, or if you just want to run these old models, you know, without any of the splitting, you can do so in this way. So let me stop there and just see if there are any questions or thoughts folks have on this topic. You should see, like I said, enormous computational gains, like efficiency gains, and you should have the same reliability.
Hey Adam, easy question. It's Greg Fonhauer. Curious if you dug into some of those edge cases on either end of the tail. You know, when it fails to produce a similar result and why, or if you haven't got that far yet.
No, to be honest, no. think we saw this and
Uh,
said, yeah, it's okay. But there are those spikes that we're eliminating. So those at the very least are part of why there's a tail. Like if you have a big spike, maybe we'll see an example of that today. If not, we can look up one of those. But at the very least, like a lot of these data points that are like well out on the tail are just those individual spikes that are now not present anymore. Mm-hmm. Travis, do you have any? I don't know. Maybe I'm unaware. You might have dove into some of these things a little deeper as well.
yes, the spikes are what I would expect to be the ones on the far edges. There's also sometimes where you do get a different model fit, and I commented about this in the messages, but I'll reiterate it. It's that this plot does not show if the differences are better or worse. We're simply comparing, do they match? But when we look at the RMSE, which is how we judge the fit of both CalTrack 2.0 and CalTrack 2.1 in 2.0 mode, legacy mode, whatever we want to call it, frequently it is slightly better in 2.1 because we are not doing a grid search, so we're able to get a finer resolution. The other side of that, though, is that since we're doing a grid search, it's not as extensive, so sometimes you might miss the optimal solution that 2.0 actually does catch. It's a bit of a trade-off, which is the kind of the price that we pay for that computational gain. No free lunch theorem.
Yeah, the no free lunch theorem. Yeah, good question, Greg. Thanks for asking. Okay, I'm going to move us along. I mean, it definitely is a different model, but I think our goal was to reproduce 2.0 as well as we possibly could. And like I said, dramatically increase the computational efficiency. We've definitely gotten feedback. In particular, we've gotten feedback from PG&E that they've tried to implement CalTrack 2.0, and they run into computational limitations on their side. And so this is literally speeding up the model by a factor of 100 if you do this. And especially with monthly data, like we said, we expect that there will continue to be a need for this. Okay, moving on. And sorry if you hear a crying kid in the background. CalTrack 2.1 near final testing results. So we have a few little tweaks that we are going to continue to make in the 2.1 model, but I think we're not expecting to see any significant differences at this point. These are kind of minor things, and if anybody wants to know, we can talk about what exactly those things are. But I just wanted to walk through sort of a sampling of the results, and we will make sure to publish like a comprehensive set of results. But just wanted to, like I said, walk through a handful of kind of illustrative results that hit on a spectrum of different use cases. Because at the end of the day, our goal here was to retain the behavior of the CalTrack model as something that can be applied equivalently to a gas meter or an electric meter, to a commercial meter or a residential meter. And because of that, we need to be making sure that it's not just residential gas that this model behaves well in and be blind to, commercial electric meters or something like that. So we've talked a lot about, I'm going to start at a familiar point here. We've talked a lot about seasonal bias in the CalTrack 2.0 model. This top plot is showing the distribution of wintertime bias, fractional wintertime bias, across 4,000 residential gas meters. And the bottom plot is showing this very same distribution of winter bias in the 2.1 model. Obviously, it's much, much better. Bias went from -7% on a population level to -1% or a little less than 1% in the 2.1 model. We also see a dramatic reduction in the standard deviation. And give me 1 second, folks. I'm just gonna try to see what's going on here. I've got an absolutely screaming kid outside. Okay. Moving on to summertime bias. Again, top plot 2.0, bottom plot 2.1. Here we see that there is, in both cases, we see, substantial negative bias in the wintertime model for CalTrack 2.0, and we see, again, some negative bias in 2.1, but obviously most of the bias has been remedied. In the summertime, the situation is reversed. In the 2.0 model, we see, more than 10%, we see 11% bias. In CalPrec 2.0, 2.1, that's cut by more than half, and bias is 5%. And medians kind of follow the same kind of pattern. But again, we see that the bias was originally positive, and it is still positive in 2.1. And I'm not showing shoulder here, but shoulder has a similar story where we dramatically reduce bias. You might ask, well, why didn't you get it down to 0? Why is in 2.1 mode, why do you still have some bias, whether it be, winter or whether it be summer or shoulder? And the answer is because we are using this penalization function approach that prevents the model from splitting into its most complex form, because doing the latter would induce a large amount of overfitting. So we're making sure that in order for the model to split by season or split by weekend and weekday, it has to overcome this penalization threshold. In other words, the benefit of splitting into an independent summertime model, for example, would have to outweigh the penalization that we're applying, that hurdle that the model has to get over in order to carve out a separate independent summertime model. So the model is basically splitting when it needs to, or when it's very beneficial, but it's not splitting all the time. So some of the meters that had a small amount of bias in the winter and the summer, for example, still have that, because the benefit of splitting and eliminating that bias and introducing additional risk of overfitting is not overcome. So I'm going to switch gears here and talk about weekend weekday bias, and we're now looking at electric meters. So these are residential electric meters, and the top plot again is 2.0. In this case, we see that there's a bias downward, a negative bias in weekend data points of -3% across the population. That's reduced to 1% in 2.1. And where we really see this weekend weekday bias is in the commercial sector, right? You have a lot of offices, you have buildings that are open on the weekdays and closed on the weekends, or vice versa. And so where we would really expect the sort of test to show up, whether or not this model is doing what we want it to be doing with respect to weekend weekdays in the commercial sector, and this is what that looks like. So the top plot is 2.0, bottom plot 2.1, and you can see that in the commercial sector, the total weekend bias was 14% positive. The model was over predicting weekend consumption by more than 14%. That's now reduced to less than 1%. And you can just see that enormous tail of really dramatic weekend bias is just totally eliminated in CalTrack 2.1. And this is exactly the kind of behavior we would hope to see. And again, I would just remind everybody that all of these results are coming from the same exact model. The same exact model is being applied to residential gas meters and is remedying seasonal bias for the most part. And that same model is being applied to commercial electric meters and is remedying weekend weekday bias. So let me stop there and see if there are any questions, and then we have a few more results to share and we can keep moving. Yeah, Greg, you have a question or thought? All right, I see your hand is raised, maybe not.
Sorry about that. That was either old or an accident. No
Okay,
question.
okay, no worries at all. Okay, so this is another plot that should look familiar to folks. The top plot again is the CalTrack 2.0. Bottom plot is 2.1. The x-axis here is the difference between the average daily temperature and the heating balance point temperature. These are all gas meters. And we're looking at shoulder on the left, summer in the middle, winter on the right. And those top three panels show the error profile of the Caltrack 2.0 model. So if we look at that top right-hand plot, for example, this is the winter time, and we see that temperatures right around the balance point temperature are subject to enormous negative bias. The model dramatically under predicts consumption in the wintertime usage on days that have balance point temperatures close to the balance point temperature of the entire Caltrack 2.0 model. Why is this? It's because people start heating their homes at higher average daily temperatures in the winter than they do in the summer. So, you know, if the average daily temperature is 60 degrees in the winter, somebody's prone to heating their home with gas, whereas that same exact temperature pattern in the summer will not yield heating, you know? And so this is one of the reasons why the Caltrack 2.0 model, we have said for a long time, is an underfit model, because it's not aware of those kinds of things. It has to constantly be splitting the difference between 60-degree days in the summer, 60-degree days in the winter, and in the end, it just kind of misses this behavior that is near the balance point temperature. We can see the shoulder months on the left have their own distinct error pattern, and the summer is just across the board. There's positive summertime bias. Now, the bottom three plots are those very same error profiles now in the 2.1 model, and we can see actually there's a similar shape to each of those. And again, this comes back to this concept of a penalization function, that really the model is split into independent seasons only when it can overcome a barrier that we've put in place in order to prevent overfitting. And so again, we've remedied something like 75, 80% of all seasonal bias is now mitigated in the 2.1 model, but these patterns still do exist. And this is actually, in our opinion, this is a good thing. It's not a bad thing, because there's no such thing, as Travis said, as a free lunch. Like, you can either, if these lines on the bottom three plots were just flat and just pinned to zero, I guarantee you would have a massively overfit model that would not perform in a reporting period. So let's take a look at a few individual meter examples. Here, 2.0 is on the left, 2.1 is on the right. This is a gas meter, and we can see exactly what I was talking about that led to this kind of an error profile. So take a look at that, again, that top right plot, where we have large negative bias right around the balance point temperature. When we take a look at our 2.0 model and we separate out the data points into winter in blue, shoulder in green, and summer in red, you can see that the 2.0 model, which is that bottom left-hand plot, and it's just that linear increasing like around the balance point temperature. There it goes, temperature independent region above 64 degrees, linearly increasing consumption below 64 degrees. That model around the balance point temperature, if you look at all those blue dots in the winter, all those blue dots are much, much higher than the model, or for the most part, they're higher than the model. And that leads to this cumulative error profile on the top, where as we go from the coldest temperatures to the warmest temperatures in the winter, we see just a gradually increasing amount of error. And this is just showing how seasonal bias arises. If we instead look at the red data points, this is the summertime, and we can see the model is consistently higher than the vast majority of those summertime data points. And that has the opposite effect. It leads to positive summertime bias. The model is over predicting consumption in the summer. The Caltrack 2.1 model has split into two distinct models. One models only the wintertime consumption. That's the blue line on the right bottom plot. And the summer and shoulder have been combined into one independent model that has been smoothed around the balance point temperature. And the cumulative error profiles are shown in the top plot. And so here you can see the winter is split out into its own independent model. Given that, you would expect there to be very little bias across the sum total of data points, and that's indeed the case. You can see that that blue line in the top right-hand plot ends at about 0. Whereas the shoulder and summer, because they've been combined into one model and not split independently, there wasn't enough benefit in splitting summer and shoulder independently to overcome the penalization function. So those two seasons were lumped together into one independent model. You can see that there is some bias that remains, negative bias in the shoulder period, positive bias in the summer period, but dramatically reduced from where it was in the 2.0 model. So again, this is just how the model is behaving. This is just a good example that we wanted to show. Greg, I see you have your hand up again.
Yeah, that does that on purpose. I have a question and then a follow-up question. Could you remind me how heating and cooling degree days are calculated? Is it based off of an average daily temperature? Is it done using kind of like the hourly method as a differential from, you know, whatever that hourly temperature is?
Yeah, so heating degree
In this
day,
case.
right? So you take the average daily temperature on a given day. So let's say the average daily temperature is 50. If your heating balance point temperature is 60, then the difference between those two things is your heating degree days. So it's 60 minus 50 in that case. So if you're 10 degrees below the heating balance point temperature, then you have 10 heating degree days. And that gets fit into that gets fed into the model and then is multiplied by the slope, the coefficient, to determine the of heating on that day.
Yeah, that's what I thought. So I'm curious if you messed around with sort of the method for determining heating degree days, you know, based on a balance point in sort of evaluating this bias. And I guess I'll use an example from where I live as for example. So I live in Reno, high desert, where right now it's been highs in the 80, like 85, but at night we still get down to 45, right? So the average temperature for the day is like 65. That's not that different from like the Bay Area, but you have much smaller differential nighttime to daytime, right? So right now, I am not, well, I personally am not doing any cooling, but if I didn't have nighttime temperatures the way they were, I probably would be, right? I open the windows at night, or maybe you don't even have to because I have no insulation in my house. Can you kind of see where I'm going with this question? Mm-hmm. The way that you calculate, you know, those differentials does impact how it correlates to people's energy use. And I'm wondering if you mess around with that in terms of, you know, evaluating bias from a seasonal standpoint. Does that make sense?
Yeah, Travis may have some thoughts here as well, but I have two initial thoughts. One is we have kind of poked around a bit at using heating degree hours and cooling degree hours, even in a daily model. So where you're taking into account the hourly temperature data, because yeah, you know, keep in mind, when you have daily data, you're obviously limited by the granularity of the consumption data, but you're not limited in the same way with weather data. You can still get hourly temperature data. Now, I think it would be kind of opening up an entirely new modeling effort in front in order to really explore like genuinely what it would look like to use heating degree, to use hourly temperature data instead of daily temperature data in a daily model. But that's something that I think we saw there could be some promise there. Having said that, I think there's no reason, in my opinion, to suspect the model is behaving poorly for the situation you described. The heating balance point and cooling balance, if we're thinking about like an electric meter, you mentioned cooling. So if we think about an electric meter, in the situation you described, I would expect that the heating and cooling balance points would be closer together than in a more temperate region. So, you know, basically what you're describing is, hey, I've got in Reno, you know, there's a bunch of days where the low temperature is maybe 40 degrees, the high temperature is 90 degrees. And so the average daily temperature winds up being 65 degrees. But actually, I'm both heating and cooling my home on days that are like that. And if that's the case, then we would just imagine the raw data, right? The raw data itself would push those heating and cooling regions closer together than you would see otherwise. And there's no reason the model couldn't perform well under such a paradigm. Travis, is there anything else you'd consider there? Is there anything else you've looked at here?
So heating degree days and cooling degree days are largely just things that we apply to the models to help us understand what the model is doing. The model at its core, it doesn't look at anything to do with that. It doesn't care at all. All it cares about is, can it fit the data, and it moves around the balance point such that it gets the best fit possible. We can then infer different things by interrogating the model. So like we can get, by looking at heating degree days, we can get heating load, and we can kind of understand some underlying features. But at its core, the model itself doesn't care about any of that. With that being said, you do mention individual hours here. And so you might recall back, I don't know, months ago at this point, that we were investigating thermal lag, where the thermal lag would actually average the days and shift it as well as to lengthen it appropriately. And we found that that doesn't actually improve model performance at all. So we just removed it from the code base, and you have what you see here.
Yeah, and that was actually kind of part of what I was thinking about when I asked this question. Was I remember you saying using thermal lag like didn't really improve the model. I mean, I guess I'm sort of hyper focused on my own situation because humidity plays such an impact in terms of like if you look at daily averages versus sort of the spread of temperature throughout the day. So in the winter, you know, we may not have as big of a as much movement throughout the day just because there's more humidity. But when it's 7% humidity in August here, you know, it might be 45 at night and 100 during the day. So yeah, there's like, I can definitely see, I know from my personal experience, like there's thermal lag, but a lot of it has to do with behavior and how I, you know, heat and cool my house. Yeah. But, you know, just noticing that there's bias in my own behavior as it pertains to seasons, where really the root of it is, I think, humidity. And, you know, maybe if we could incorporate some of those other weather features in there, it would help sort of resolve some of this. Does that make sense, or am I kind of off base?
I think it makes sense. I think, Greg, what we've paid really, really close attention to throughout this effort has been making sure that if we introduce a new parameter into the model that gives the model, you know, more flexibility, that we're only doing so if we're confident that in the majority of, well, not in the majority, we're only confident that we're not going to make the model yet more prone to overfitting. And humidity is one of these things that I think is worthy of investigation. You know, it would absolutely be worth spending some time and effort and seeing if, you know, the incorporation of humidity would make a big difference. You know, thermal lag, like Travis mentioned, is a real thing. Like thermal lag is real. I mean, we definitely observe thermal lag. The reason that we removed thermal lag from the model this time around is, you know, we don't want the perfect to be the enemy of the good. We could spend years like trying to figure out the best daily model. It might be something that we come back to. It might be something we come back to in the hourly model as well. But like all of these things are absolutely worthy of kind of investigation. You know, one of the things you mentioned is, you know, or I don't want to put words in your mouth, but I think I heard in your comment that, you know, humidity can be like a seasonal thing. You know, you get a lot of humid days in the rainy season, for example. And if humidity is driving changes in behavior or changes in consumption patterns, then then the model should naturally split into a different seasonal model for that season, if that's the case. So I think it's an indirect tool, like allowing the model to split by season is an indirect tool. But the question sort of becomes, when you have enough overlap between these things, that in the vast majority of instances, or at least in the, you know, the reasonable majority of instances, you're actually accounting for that behavior reasonably well. And so, I think the place we would start would be like where we started with this whole process, which was looking at the Caltrack 2.0 model, seeing where we had the biggest sources of bias. And we did not in that process look at humidity specifically. Like, is there a large bias that is induced in the 2.0 model due to humidity? Does that bias still exist in the 2.1 model? What I would encourage folks to do is all of this code is going to be open source in a matter of a month or two. And if you have a data set that you want to look at, like, the group is going to hopefully continue to stay on the rails, and like that would be an awesome project for somebody to look at. So not sure, Greg, if anybody over at Franklin would be interested in kind of partnering on some of that kind of R&D, but would welcome that.
If I can interject for a moment. So we actually have been working on some preliminary work on the hourly model. So one of the time series, obviously, that we use is temperature. We've also looked at adding in additional time series, such as humidity. And we found that actually it doesn't improve the predictive capabilities of the hourly model. This is not final, obviously, it's preliminary work. But basically, the reason is because the humidity basically follows the same exact trend as temperature by and large, so you don't really gain much information by adding it in.
It's like if you're saying it's correlated, Travis, like humidity and temperature can be very correlated.
Highly.
Interesting. Yeah. Good questions, Greg, and good thoughts. All of these things, I just want to make the point again that the intention here in developing the Caltrack 2.1 model is not to have it like live in stone from now into perpetuity. It's to develop, one of the reasons we're starting with Caltrack daily is we thought that we could get something on the rails here that would allow us to start like versioning these models. So there's no reason why further R&D can't be done in the future. But we do need to kind of like take the progress that we've made and say, okay, like these, the biggest problem in the Caltrack daily model for a long time has been seasonal bias in gas meters specifically. And so one of our big focus here was like making sure that we solved that problem. But we're definitely, it's not a perfect model. There's more that could be done. I would just say to anybody who's interested in doing this kind of testing, I've browbeat you enough on this topic, but I'll just say it again. You've got to pay attention to the predictive capacity of a model. It's not enough to just say, oh, when I add another variable, I see a better fit. Like that is going to be the case if all you're looking at is training data. You need to pay attention to test data sets. That's the big reason why, one of the reasons why this has taken a while on our end is the establishment of cross-validation, the testing and refining of a penalization function, the optimization of those parameters that feed into the penalization function. Okay, I'm gonna move us on here. There's a few other, I think, very interesting examples that I just wanted to showcase. This is now, so we're switching from residential gas to commercial electric, and this is now looking at weekday differences. So the black data points here are weekdays, the blue data points are weekends. And the Caltrack 2.0 model shown in that bottom left-hand plot is splitting the difference between the two because it's unaware and it's not able to be aware of whether a day is a weekend or a weekday. So that top plot shows you that, basically there's just a high degree of, positive weekend bias when the model is over predicting consumption on the weekends, and then balancing that out with high negative weekday bias. When we see the model over predicting on the weekends. And another thing I want to point out here is just for those who are maybe staring at this Caltrack 2.0 model, if you can take a look at that range above the cooling balance point temperature that's around 79 degrees, you see the model kick up into a temperature dependent region that simply is not there. Like if you look at the raw data, it's really clear that there is not a temperature dependent region of this meter's consumption pattern. The model is getting fooled into thinking there is because all of the hot days are occurring on weekdays. And because it's pushed down in order to split the difference between weekends and weekdays, it thinks there's a temperature dependent region. So one of the points I want to make about weekend weekday bias, you can say, okay, look, the Caltrack daily model really is mainly used for the calculation of maybe monthly savings or annual savings or something like that. So it's not necessarily critical that, you know, the model is aware of weekends and weekdays, but when you have behavior like this, it's clear that the weekend weekday bias actually has ramifications beyond just, you know, being a poor fit to any one individual data point. Like, we actually see this behavior in more meters than I was surprised at how many meters showed this pattern. You know, by the way, like, if this meter is showing this pattern, it means that a whole bunch of other meters that are in that same, you know, in that same region are experiencing the same temperature patterns. You're bound to get a lot of this kind of thing happening. Another thing I would point out is, like, if you stare again at the Caltrack 2.0 model, you can see those spikes that we were talking about. So those spikes around like 58, 59 degrees and around 50 degrees, those are real spikes in the Caltrack 2.0 model. Those are obviously not there anymore. So, you know, comparing this to the graph on the right, the Caltrack 2.0 model is split into weekday, weekend. And so there's basically no weekend weekday bias to be found in the Caltrack 2.1 model. Okay, I'm going to bring us on to our last example here, and this is kind of brings a lot together in one set of figures here. So again, Caltrack 2.0 on the left, Caltrack 2.1 on the right. Now, this is an example of a model that was split by both season and weekend weekday. And if you just look at the observed data points on the bottom left-hand plot, you can see that they're all color-coded by summer weekday, winter weekend, winter weekday, those kinds of things. And there are multiple patterns to observe here. So if you look at that set of data points, the like orange, red, black data points at the bottom, kind of around 100 kilowatt hours a day, all of those data points are on weekends. Meanwhile, the winter weekdays are shown in that olive color, and they kind of have their own, like, clearly their own pattern, and it's distinct. Meanwhile, the shoulder and the summer weekdays are shown in green and blue, and they have, you know, kind of a separate and distinct pattern going on. So the cumulative error profiles of, you know, winter weekend, winter weekdays, summer weekend, summer weekday, they're just all kind of form this like flying V pattern. You know, I feel like I'm watching Emilio Estevez here or something like that, and the Flying Ducks. Like, that's what that graph reminds me of. The Caltrack 2.1 model, you know, had a reason in this case to split by both season and weekend weekday, and it did. So the 2.1 model has an independent model it's a temperature independent model, or nearly a temperature independent model for the weekends. And then winter weekday and summer shoulder weekdays are split out as independent models as well. And then I'll point out one last thing, because this is going to set the stage for what Travis is going to talk about here. If you can look at these cumulative error profiles, and you can see that on the winter weekday, again, that olive color, there's kind of a stepwise function around 52 degrees where the cumulative error increases and kind of then stays constant. If you look at the bottom plot, you can see there's two data points that are just sitting at 0. So this meter had 2 data points that were just 0 consumption. And the reason we're seeing a stepwise increase in the error profile here is, like, technically, we're using an adaptive loss function that Travis is going to speak to here in a moment. And B, that adaptive loss function is determining that these data points are significant outliers and need to be downweighted in the model. So a lot is going on in this one individual meter, splitting by season, smoothing. You can see that the shoulder summer weekday model in the Caltrack 2.1 is smooth. We have an adaptive loss function that is downweighting a couple outliers. We have an independent weekend model that is split out from the rest. And so I'll stop there, and I think we'll hand the baton to Travis here to talk about adaptive loss and our recommendation around adaptive loss. Travis, I'll just keep the deck if that's okay with you.
Yeah, that's fine. Do you want to go over this table before I start talking about the conceptual?
Oh, sure.
Parts.
I'm happy to speak to this. So, when we left the topic of an adaptive loss function a few months back, we basically said, look, this is something we're interested in, but we want to formulate the model and then come back and validate the adaptive loss function against a more routine, like sum of squares optimization function. And the thing that we need to pay very close attention to is whether or not the adaptive loss function is inducing bias in the model. I'm not going to go through this entire table of numbers. I will just tell you that in no instance do we see the adaptive loss function inducing substantial bias. And so we're looking at, all of these different weekend, weekday, the differences between adaptive loss and other versions of the model are pretty minor. So ultimately, we've had our concerns like largely alleviated that the adaptive loss function itself is going to introduce specifically annual bias into the numbers. That's really the thing you need to watch out for the most. And then there are some advantages of the adaptive loss function. I could keep speaking to this, but I think Travis will hit on those. So upshot, in order to keep pursuing the path of like an adaptive loss function, we wanted to look at all these cases: commercial electric, residential gas, make sure that we weren't inducing annual bias in the model on account of downweighting outliers. There are positive and negative outliers. So you could imagine a symmetric downweighting. And that appears to be the case, that it is fairly symmetric. And so we're not seeing an induction of annual bias on account of using an adaptive loss function. Okay, Travis, passing it to you.
All right. So this gets back to what I've been saying for months now, and that is that when we look at these models, we have to understand that it is not about how we fit them in the baseline. Is that somewhat useful to understand how well the model is doing? Yes. But ultimately, we are using these models for predictive purposes. So what I'm showing right here is energy usage versus temperature. And on the left is there's no outliers in winter, so it's capturing what's the bulk of the behavior is well captured. But if you look on the right side, and this is kind of showing what Adam was just talking about in that prior example, well, not even an example, but an actual meter. And that is that if you have outliers that are quite low, 0, then at some point it will pull the model down because it is in a sum of squared errors. So those are actually being treated with more emphasis than these other points, because you are squaring based off of the residual. And so since those are so far away, the residual is high, you square them, they become even more important than the bulk of the data. So our approach to this is, well, what if instead of using sum of squared errors, we use an adaptive loss function? This is even a step beyond using mean squared error, which would be like an L1 loss function, because what we do is this plot here on the left shows the loss response versus the number of standard deviations away from the mean. And this is the version of the adaptive loss function which is penalized based on the shape of that loss function. So if we're looking at sum of squared errors, it's this black curve, and you can see that it is actually the smallest loss response when it has no residual at all, which is great because that's exactly what we want. If the outliers are basically non-existent, then we do want it to follow a sum of squared errors approach. However, on the other end of things, you see a Welsh loss function, and that is shown in purple, where it is the lowest at 0 standard deviations away from the mean. However, it also basically downweights everything beyond about 3 standard deviations to where it has no more effect on it. So we've gone from one extreme where sum of squared errors is putting an emphasis on decreasing those outliers as in terms of the overall model, whereas the Welsh loss function is saying those don't matter. Let's just fit the bulk of the data. And this is all based off of a statistically justifiable metric. These are not arbitrary numbers that I've placed in between these to define where these lines fit. And this is also a continuous function. So we are able to replicate all of these losses from alpha is equal to 2, which is sum of squared errors, or L squared, all the way down to a Welsh loss function, which is represented whenever the alpha is at negative infinity. Okay, that's all really complicated. On the right is a much simpler idea of how this is working. So if we look at the summer months that I just showed you before, we still have all of those points there at the bottom. But instead, this time, we say, well, we're not going to go with the sum of squared errors, so we're not going to allow it to be pulled down. Instead, we're going to downweight all of these in the most intelligent way that we can based off of this adaptive loss function I just described. And so you would end up with getting something more like what I have here in orange, where it's actually going to fit the general behavior of the data points. The argument against this is what Adam has already addressed. Are we introducing bias? But then, one, we're not really introducing bias, which he's already shown. Two, we have to understand the purpose of these models. It is not for us to be able to put a temperature in and to be able to get the best result from our baseline year. That's marginally useful in some cases, but not for what we want. We want to be able to put that in for next year to be able to understand what this building most likely would have consumed as far as energy goes, whether that be in therms or kilowatts, and then to be able to get that result back so that that is our baseline, which is what the adaptive loss function is accomplishing. And back to you, Adam.
Thanks. So any questions on the adaptive loss function? I think I'll just say Travis and I had a bet. We had a wager on this. I thought that we would see some bias creep in. We did not. So that's a good thing. So I think, it appears as though we can kind of have effectively the best of both worlds, which is to have better model predictions on an individual meter basis without biasing population level results. And it's something that I think means this model can work both on a population level, just as it should, and also be a better predictive model even on an individual meter level. So are there any, yeah, Will, I see you have a thought or question.
Yeah, I was just curious about, did I miss it? Did you say which loss function you ended up using at the end of the day?
Yeah, Travis, which of these functions here, or is it some mix of these?
So it's adaptive. What it does is it actually figures out what the best alpha is for the data set that it's looking at. So that alpha changes for every single meter. Sometimes, like for winter, let's say if winter were its own model, it would pick sum of squared errors, whereas for summer, it might pick a number that was like, I don't know, 0.5 or something, which would be somewhere between a Cauchy and a smoothed L1 response.
Gotcha. So it's fit for each meter?
Correct.
Hyperparameter. Okay, gotcha. Oh, sorry, I meant to take that down.
It's all good. Any other thoughts or questions on this or anything we've covered to this point? Because we'll switch gears here in a moment. Okay. thanks for nerding out with us on all of this to this point. Now I think we can all take a deep breath and think about final steps here. So nails in the coffin. What needs to happen between now and sort of officially releasing CalTrack 2.1? Basically, we have some like little tiny model tweaks that we're making, just kind of finalizing them and testing them. We'll kind of run through the whole modeling exercise again on these 6,000 meters that have been the basis for testing, and do just final validations and all that kind of stuff. Then we obviously need to have documentation. These are methods that we've talked about a lot, but we need to get like rigorous text in place that says, here's the recipe for how you operate CalTrack 2.1, similar to the methods, how they're delineated on CalTrack 2.0 on the website right now. So we need to emulate that for CalTrack 2.1. Code cleanup, obviously, this is not just a methodological set of questions. This is a code, exercise, and so we need to incorporate code into the OpenEEmeter, or at the very least, at this point, get code ready for people to review and test. And so I know that Ethan has already said he'd be interested in. And I see your comment, Ethan. Thank you for. I'm always nervous about like volunteering people here because I know this is a lot of work. But we would definitely welcome your like code testing and reviewing. So just Ethan, by the way, and for anybody else who's interested, we're in the process right now. Like we're on this step right now. Travis is cleaning up the code. We're working with one of our engineers to get the code packaged up into a way that we can incorporate it into the OpenEEmeter repository and create a branch and share it. So would definitely welcome your involvement there. I think Steve Sufian has also voiced some interest in being like an external code review and tester. And if there is anybody else, just reach out. Oh, Steve, you're here. I figured you were in Paris. I was like, I'm going to say something either nice or bad about Steve, and we'll figure out if he's actually on the call.
Got back yesterday. Thanks for the invite there.
Awesome. Yeah, I talked to McGee, Steve. I hope that it's okay that I'm putting your name out there. Okay, we're looking forward to working with you on that. And by the way, welcome back from Paris. Maybe at the end of the meeting, you can give us a little briefing because you were there for the LFE, right?
I got stickers.
You got stickers, man. Send them around. Great.
OpenEEmeter stickers, yeah.
Whoa, dang, that's cool. OpenEEmeter stickers, really? Dang, that's pretty cool. And then we need to seek approval from the technical steering committee. But hopefully, like if we've done our jobs well, seeking approval from the technical steering committee is more like, hey, here it all is, let's get it incorporated, and there really isn't like a debate to be had. So, but that's why we got to focus on these first 4 steps, because we're not ready to seek approval from the technical steering committee yet. We need to get external review, testing, those kinds of things. And then the question of like what comes next. So I think I would just kind of open up the floor here right at the moment to just ask people on the call, if you've been part of this process, has it been good, bad, ugly? Has it been, too much of me just blabbering away? Have you found it informative? Have you found it useful? Like, what would you change about it? Should it continue? If anybody's brave enough to kind of offer some, constructive criticism or we take compliments too. If anybody has any thoughts on the working group to this point. Thank you, Steve. Well, if you have anything that comes to mind, we got a little more time here. I'll keep at it for the moment. Yeah, Steve. Yeah, go ahead.
Yeah, I wasn't sure whether, but we can talk about this after you finish all your stuff, but I just had some questions, comments about kind of EEmeter code development next steps. But do you want to talk about that after everything?
Yeah. Yeah, I just have 2 more slides, Steve, and then let's talk about that.
Sounds good.
So just setting the stage here, I think one of the areas we would like to venture into is the CalTrack hourly model. And so I'm just showing a plot here of something that Armin over at Recurve has been working on, which is, so let me just say quickly, the hourly model. What are the variables that feed into the hourly model? There's time of week and there's temperature, and then there's like an occupancy parameter that gets determined, and there's a couple independent models, and it's an annual model kind of thing. Now we haven't really specified this model for demand response at this point. And obviously, there are more and more solar PV customers on the grid, and those solar PV customers are critical for demand side programs. Those are the very customers who are likely to get battery storage retrofits. Those are the very same customers that have an opportunity to feed back into the grid and shave peak if they have a battery. They're more likely to get an EV, things like this. So these are customers that it's high time we're better able to model than the current Caltrack hourly methods without being aware of solar irradiance or any other like solar variables can handle. So this is just a graph of like a very preliminary model. He's just kind of poking around, and the blue curve is the AMI data. This is a solar PV customer, or I'm sorry, the green curve is the AMI data. And he has disaggregated this AMI data into a solar PV generation trace, which is the orange trace, and like a whole building consumption profile, which is the blue trace. So, we're very interested in being able to disaggregate solar PV, but even more fundamentally, just being able to produce accurate and reliable counterfactuals for customers that have solar PV on their rooftop. So this is a big area that we'd like to venture into so that Caltrack doesn't have this limitation where it can't model solar PV customers. And like I said, also bringing this around to some of the demand response conversation. And then lastly, I think, and Steve, maybe this kind of sets the stage for your thoughts as well. We're interested in just a consolidation of our open source code packages that, so right now, like the Linux Foundation has under its umbrella the OpenEEmeter. And so part of this project is updating the OpenEEmeter with the Caltrack 2.1 code. Now, there are other open source projects that are really, really critical to the measurement and valuation of demand side programs, including the grid meter, which is the code base, the open source code base responsible for conducting comparison group sampling and comparison group savings corrections. And then there is the flex value code base, where we've taken avoided cost data and you can take hourly savings outputs and calculate the GHG savings and the avoided costs associated with those savings. And that's an open source code package. And all of these open source code packages live in different areas right now. And some of them are part of LFE, some are not. So, we're thinking about trying to consolidate a lot of this stuff and get users of these code bases to a point where they don't have to like create all of this glue on their own. But a lot of it is just kind of consolidated in one spot where it's like, hey, here's how you calculate savings for a demand side program, and here's how you value those savings if you have avoided cost data. I'll stop there. We're just wanted to plant some seeds around this to see if people were interested or would see this as valuable, or if people had concerns about this. Are there concerns about bringing in grid meter code, for example, into this conversation and into the LFE? So any thoughts folks have? And Steve, maybe we can start with you on your thoughts on EE.
Yeah, so two different kind of lines of thinking. On this, what you were just saying, I've had some experience now with another LFE project, the carbon data spec. And from what I've seen there, they kind of have, like within the carbon data spec, which OpenEEmeter is kind of on that level, they have two pretty distinct working groups that are interrelated. So we're doing like power systems data standards and like customer data standards. And so I could imagine under OpenEEmeter as the project, being able to have, like, you could have a EEmeter working group. I think GridMeter makes sense as another working group in that kind of space, just because at least those two libraries are pretty tightly connected. Like, I mean, GridMeter sort of assumes you're using EEmeter to calculate this. Maybe it doesn't, but like they seem pretty tightly connected to me, at least. And then just to make it easier, you could put flex value there too. That one seems a little bit slightly different in terms of like what it's working on, but it's still like a per meter kind of thing. So I would imagine probably the simplest thing would be to like make a working group for each of these and then kind of coordinate all the code within LFE. But I can't really think of, other people might have reasons why that might not be a good idea.
To clarify, are you saying these would all be independent working groups, but it would all live within the same framework? Or are you saying to keep the framework separate?
Yeah, I would say so the framework being like OpenEEmeter as the project in LFE. And then right now, I think there's only one working group in the OpenEEmeter project, which is this one. And so instead of just having one, this one is the like you could call this one the CalTrack and EEmeter, or we could even separate it out into 4, right? You could have a CalTrack spec working group. I know that like specs in LFE are pretty different from code, and so that's kind of an LFE question. But you could have conceivably each of these be its own working group, and then you would coordinate between them, right? CalTrack puts out a spec, EEmeter references the spec and implements the spec. You know, GridMeter is a different working group. You'd have leaders of those working groups interacting with each other to make sure things are aligned. That seems to be how it seems like that. That's the vibe that I'm seeing it happening in this other project I'm in. So, but I'm sure there's other ways to do it.
That's a good thought, Steve. So like, I mean, I think it's hard to imagine trying to sort of cram more into what we've done in this working group. So it's hard to imagine saying, okay, this very same set of people now needs to pay attention to flex value and GridMeter and OpenEEmeter.
Yeah.
And there are different areas of expertise as well. You know, I could definitely imagine somebody coming to the table and saying, hey, I've got some input on avoided cost value streams that are being, you know, put together in New York or something like that. And that's really neither here nor there as far as CalTrack itself is concerned, but is a topic that needs, you know, its own kind of care and consideration. Yet at the end of the day, these things do tie together because, you know, we're really trying to help the grid and trying to help save carbon. And, you know, so you've got to have some kind of way of converting savings calculations into dollars and GHG. Same thing with comparison groups, right? So I think your point is well taken.
Yeah, so that's my kind of initial thought on terms of how to structure it, like bureaucracy wise. That my other question was around, and I can help with this when we get into the code stuff for EEmeter, but just I think one of the things that would be nice to kind of get when we get to integrating it into the actual code, we should probably do things like I just upgraded it to Pandas 2.0. I think we should probably get some like typing into the Python, you know, like kind of modernize the code base since we're going to be updating so much of like the internal code anyway. And so I'm happy to definitely help with that, but there's I think I'd propose like kind of a push to kind of like upgrade us to kind of, you know, standard Python 3.10, 3.11 kind of rules, since we kind of are doing like a big code rewrite anyway. And happy to help with that part. Yeah, and yeah, my last question is sort of like, version bumping is another thing, but I can talk to Jason. Would be the person that's kind of like most involved in the actual like code base management, right?
Yes.
Okay, cool.
To what you just said, I think that that is a fantastic idea. Jason and I are talking about how to integrate this into OpenEEmeter as is. And one of the primary places that Jason's contributing right now is to figure out making sure that the inputs to the new CalTrack 2.1 is roughly lines up with expectations from OpenEEmeter, as well as the outputs. I am changing my outputs a little bit in that I am no longer just exporting an array. Instead, I'm exporting a data frame that has like model, heating load, cooling load, uncertainty, all of that, so that it's just kind of packaged together, and you're retaining all of the date time information as well for all of that.
Yeah.
So I do agree that we should update this as much as possible to get it up to the newest versions, as far as we can get them at least.
And I think I think changing outputs is fine. You know, that's major version bump, right? And write up the docs and make sure people know to be warned.
Yeah.
I mean,
it was also with some thought to what do I expect us to be wanting to output on the hourly model as well. And I think that a data frame makes sense, as well as like the same general structure, so that once we hit that stage, then that will basically be all of CalTrack or OpenEEmeter has been updated. And so it'll just all follow this new output paradigm.
cool.
I think we got your pull request finally in, Steve.
Yeah. It's
Yeah.
been merged.
Sorry,
Now I just need
sorry
to.
that took so long. You know what?
No
It's like
worries.
embarrassing. What actually happened over here is Phil was like, yeah, I've handed the reins to Jason. And then I followed up with Jason, was like, Jason, you know, what's going on? Why is this, you know, can we get this in, please? And Jason was like, well, I don't have write access.
That's what
So
that's what I thought. Yeah.
yeah, so
No, it's not
our
your
bad,
fault,
man.
Phil.
Sorry,
Yeah,
it was
I
just
think I
the
was-
cross wires over here. Oh no, it's not your fault, Phil. It's just kind of a funny here. I mean, we're all working on a volunteer basis, right? I mean, that's just
Wait, no worries. But if I've got everybody in the room for another plug, PyPy versioning. Does Jason also have access to that key? Can we bump a version at some point?
Phil, if you're on, you're really the one to speak to that. I'm over my head here.
Yes, he has access.
Yeah.
And yes, Jason, we should do a version bump for Steve.
Awesome. Sounds good. Definitely agree.
I will trade you one OpenEEmeter sticker for it.
Honda, yeah. Okay, well, it sounds like there's more to come on that front. I mean, definitely, like, this is just good hygiene, right? Like, let's bump versions, let's get stuff, you know, updated. We don't want to be on old stuff that's going to be deprecated and all that kind of thing. And Steve, I don't know if you've seen some of this stuff also with like Pi Arrow, with like the new Pandas version. Has like much more efficient data handling and storage. So we've been experimenting with some of that. Brian Gerke over here in particular has been exploring kind of like how we can you know, use these virtual machines that have memory limits and still operate on large data sets in a Pandas environment and stuff like that. So there's some cool stuff there that, you know, eventually we might want to bring in. Okay, cool. Any other, so I feel like we're, you know, one of the things we did not talk about today, there are still some outstanding topics on sort of the CalTrack 2.1 front with respect to delivered fuels, some of the DR baselining stuff, Steve, whether we push that into 3.0, we can push that stuff into 3.0. Like it's, like I said, I don't think there's any reason we have to worry about, like, we can update as things come along. But I do feel like we're coming to sort of a end of this chapter in a way. And it's worth kind of just acknowledging that, hey, you know, Steve, you submitted, you know, this pull request. We got these updates in. We got the EE weather updates in that the folks from Carbon Co-op worked on. So all of this stuff I think can work on like UK at this point. No, is that not in yet? Jason, Phil, do you have any, what more needs to be done there? Not to put you on the spot, but what else needs to be done on the UK stuff?
Off the top of my head, I think for OpenEEmeter, I believe James just wanted to update the tutorial. I think weather there's a couple more outstanding pieces.
Okay, let's follow up with them and just make sure that that doesn't die on the vine.
Yeah.
Yeah, I'm sorry, I lose track of like where we are with everything. And then obviously kind of like the big ticket item here was, CalTrack 2.1, the daily model. And I think we're coming to a very good place. We haven't solved every problem. We probably never will, but people have raised some really good points about looking at, humidity, looking at, continuing to, keep in the back of our head like thermal lag and maybe coming back to that problem. There's other types of model formulations that I think we're interested in. So we shouldn't treat this as like the last daily model that will ever be written. But I will say, I think we've come a long way in that the CalTrack 2.1 daily model is much more reliable and a model that solves some of these like big ticket items that have been present for a long time. And we've done so in a way really courtesy of Travis that is intelligent. We haven't just thrown every weekday variable, every season variable like at the model. We've paid attention to overfitting, and we've put a penalization function in place so that the model is able to take on additional complexity when and only when it really benefits the predictability of the model. And we've switched to a global optimization function and like an elastic net regression in order to determine like the heating and cooling balance point temperatures and slopes. And that's made the fundamental CalTrack 2.0 model run 100 times faster, which is not a bad deal. So I think we can feel good about where we're at, and we'll keep everybody posted on as we work toward some of these very last steps that are outlined in this slide. We'll keep people posted. For now, just keep send us any other thoughts or feedback. If folks have feedback that they didn't want to share here like in public, just send us an email if you have other things that are on your mind, and we'll look to kind of finalize some of these other topics like the EE weather piece and come back to the group on the distributed fuels conversation, because I know that was kind of left open. And if there's anybody from Sealed on the call, I think we're looking to you to carry that conversation forward. So with that being said, I think we can end a little bit early today. I want to say thank you to everybody for participation. Steve, actually, let me give you the final word. Is there anything you'd want to share with the group about your time in Paris? What was this meeting that you went to? Is there anything relevant for us? Or did you just come away inspired and ready to contribute?
Yeah, it was really cool. It was the LF Energy Summit. So it was all of representatives from all the different LF Energy projects were there. It was a lot of conversation around measuring carbon. There was power flows, a lot of really cool stuff around how to measure the carbon impact of software. So there's some of the cool groups. There was like the Green Web Foundation and the Green Software Foundation. I met a lot of people using OpenEEmeter.
Nice.
And I told them about the working group. Like one example was I was talking to somebody randomly, and they were just talking about how I think they're in like Finland, and they like were working for a client, and the client was like, hey, you need to measure this using OpenEEmeter. And so they had just a few weeks ago started working with it for the first time. So I was like, whoa, it seems like it's definitely being like growing in usage and all that. And so told them to join the working groups, check things out, told them if they had any questions, they could ask me and I'd forward them along. I also got some of these stickers.
Look at that. Dang.
I told Phil I'd send one to him, but I can send one to you, Adam, and a few other people.
Yeah, definitely send them along. That's great. Thank you, Steve.
Yeah, it was cool.
But want to say thanks to everybody again, and we'll see everybody next time around.